Hello everyone, my name is Pranjal Gupta. I'm a master's student at the University of Waterloo. Today I'll be presenting a work on columnar storage and list-based processing for graph database management systems. In this work, we explored the applicability of existing techniques from columnar relational database systems and also proposed new solutions to adopt them in context of a native graph database management system. We base our work on GraphflowDB, which is an in-memory graph database system optimized for performance and scalability that we are developing at the University of Waterloo. Graph database management systems are read-optimized systems that are known to support read-heavy workloads containing large number of many-to-many joins. These systems are tuned to perform fast joins on many-to-many relationship that is a unique characteristic of the graph data. They are able to do so by making use of adjacency list that maps a vertex to its set of neighbor vertices and corresponding edges. Typical applications for GDBMS include fraud detection, recommendation system, and social network analysis. To establish the relevance of columnar techniques for GDBMS, note that columnar stores too are optimized for read-heavy workloads that involves reading and processing large amount of data sequentially. They employ a number of techniques. First, tables are stored column by column and not row by row, which allows sequential read of values of an attribute from all rows with good cache locality and reduced number of IOs. They employ specialized compression schemes for each column based on the type and distribution of data in that column. They also process the data in blocks as opposed to row by row. Consider a query to count number of persons in a city and a simple plan that scans the city of person, filters, and finally aggregates. In traditional volcano style processing, this happens tuple at a time, starting from P1, P2, then P3, and finally P4. This does not exhibit good cache locality as reads are random. In comparison, block-based processor reads all of the person's city column together, then it filters and finally aggregates in a tight loop. Here, sequential reads on chunk of data leads to better CPU utilization. These techniques are highly relevant in context of GDBMS and can make them more competent. However, as I demonstrate next, they cannot be directly applied as the two systems differ in their data access patterns and workloads. In this talk, I'll demonstrate only two differences. Others can be found in a paper. The first difference is that the two systems differ in data access. Columnar systems are optimized for queries performing sequential access on large chunks of data. A textbook query can be one heavy on filters, group bys, and aggregates, like the one shown here, which counts the number of persons in each city. For this, the system simply reads the city column sequentially and counts two groups of values in it. In contrast, a typical query in GDBMS is like finding friends of a person and operating over their properties. Such queries do access large amount of data, however, they do so randomly. Consider a one-hop query which reads the age of Alice's friends. Our plan scan all persons, filters Alice, then joins it to neighbor nodes and read age properties of that nodes. Suppose we have filtered Alice, then the join operator reads the first element from Alice forward adjacency list and then read the age property. This happens for other values too in the adjacency list. However, as we see, reading properties are random. One implication of this difference is that the compression in columnar stores need not support decompressing random elements from a compressed block since the reading is sequential. Whereas in graph systems, needs random access for which they should be able to do random reads in compressed block efficiently without decompressing the block. Hence, columnar compression techniques cannot be directly adopted. The two systems also differ in the nature of the joins. The joins in columnar RDBMS are dominantly primary key foreign key joins which do not grow. That is, there is no explosion in the number of intermediate tuples and also no data replication. However, in graph system, joins are typically many-to-many, where join grows rapidly, and the number of intermediate tuples explodes with lot of replication that increases with the number of joins in the query. Same is shown in the illustration where we find Alice friends of friends. The intermediate tuple grows from 1 tuple to 9 tuple, with Alice repeated in each tuple. As I demonstrate later in the talk, block-based processors employed by columnar stores are not optimized for growing joins because of data replication, so they cannot be directly applied. I'll limit the differences here and next move on to the contribution of the paper. Columnar techniques cannot always be directly applied and hence requires redesigning to suit our requirements. Our work study these requirements and proposes new design across storage, compression, and query processing. We identify techniques that are directly applicable, for example, vanilla columns for vertex properties and dictionary encoding compression, where Direct application is not feasible. We design new techniques like the single indexed edge property pages, a new edge ID scheme that can be highly compressed, and a null compression scheme that allows random reads from compressed data. We also propose a new processor called list-based processor. For the scope of this talk, I would only discuss list-based processor. Other techniques can be found in a paper. To motivate our case for a new query processor, we first revisit the design of the block-based processor. Traditional block-based processor falls short of being performant on many-to-many joins. That is the USP of graph data. Consider a two-hop query on person nodes with a filter on age property of first node. I use a simple left join plan that scans the person, filters by age, and joins from A to B and B to C. The block-based processor starts with a single vector with all person node IDs. It then reads the age column and performs filter sequentially. The result of the filter is stored in a bit mask operator. It will then join all nodes in vector A to the elements of their forward adjacency list by copying them in vectors R1 and B. Hence, here only part of the intermediate data chunk is shown, but as can be seen, P2 is replicated twice and P3 thrice. That are the sizes of their forward adjacency list respectively. Similar replication happens on the next join too. Hence, the shortcoming is that there is high replication of data in intermediate data chunk, reason being that the intermediate data chunk is represented as a set of flat tuples in a single group of vectors. Each row in the data chunk is a resultant tuple. Momentarily, as I show, this can be fixed by factorized representation. Also, if we go back a bit, notice that the contents of R1 and B are exact replicas of adjacency list P2 and P3 that is kept in memory for an in-memory graph database management system. Hence, we can prevent this materialization of adjacency list. Therefore, the second shortcoming is that block-based processes copy exact replica of adjacency list in the intermediate data chunks. We address the shortcomings with our list-based processor that is based on two key concepts. First, we use factorized representation that was given by Altenio in 2016 to secondly represent joins as a union of product of independent components. Using this representation, the intermediate data chunk after one join of query in last slide can be given as a union of product of two components, singleton lists P2 and P3 and forward adjacency lists P2 and P3 respectively. Second, our implementation uses list groups. In our implementation, a single intermediate data chunk is made up of number of list group, which has three properties. It can either be a single value or a list of values. Second, the size of the list group is not fixed and takes the size of the adjacency list that it holds. And third, that they do not materialize adjacency list and just hold the pointer to the relevant adjacency list. We now run a simulation demonstrating our list-based processing. Consider a two-hop query and the same query plan as we used before. The scan operator creates a new list group called LG1 with a vector A containing person nodes. Each list group has a current index that is either 1, which means that the tuples in the list group are part of the intermediate data chunk, or it can have a positive value, meaning the list group is flattened and only one single tuple is considered in the list group. Currently, LG1 is unflattened. Next, the filter operator operates on the unflattened LG1 and reads the age property for nodes in A and evaluates the age in mask vector. We then move to join, which does two things. Firstly, it flattens LG1 by setting current index to 1, since 0th location is filtered out. Now LG1 is interpreted as a single tuple. And then the join creates a new list group called LG2 and reads the adjacency list of P2 into R1 and B. Overall, flattening of LG1 prevents the need to copy tuple in LG1 with each tuple in LG2. Also, we avoid materialization of R1 and B by instead having pointers to forward adjacency list of P2. The second join follows the same operation. It flattens LG2 by setting current index is equal to 0 and creates LG3 that points to adjacency list of P3. The factorized representation at this point is a product of P2, forward adjacency list of P2, and forward adjacency list of P3. Going forward, the second join then increments current index of LG2 and reads adjacency list of P4 to LG3. We experiment list-based processing on LDBC, which is a popular benchmark for evaluating graph systems along with other data sets. To sum up, we get a minimum speed up of 3x and maximum 19x. Complete evaluation can be found in our paper. So to end the talk, I would like to point everyone towards a project page, GraphflowDB, which contains our past research and talks. Thank you.